So our fourth topic is to do with the sectional properties of the materials. And when we are doing the sectional properties of the material, what we are going to be dealing with is a number of basic geometric properties of the cross-section of the structural members. So in this section, we are going to deal with the geometric properties of the structural members, like the center of the gravity, the centroid, the radius of gyration, the second moment of area, and also the elastic modulus of elasticity, all the Young modulus of elasticity. But without wasting time, I'm going to start off with the first case, which is the center of gravity. When we're looking at the center of gravity, this is a point. That is something that you need to know. It is a point. And this point locates the resultant weight of the system of a body or a particle. So the point at which the resultant weight of the body seems to be acting is the one that is termed as the center of gravity. And from this definition of the resultant force, we can see that the sum of the moment due to the individual particles weight about any point is the same as the moment due to the resultant weight located at G, as you can see from the diagram. That is, we have a weight of 1 Newton at section A, as you can see from that diagram. We have another weight of 3 Newton, that is at B. And then at G, that is the point whereby we have the resultant weight is 4 Newtons. So the movements, the resultant force, the sum of the moment of each particle at different locations, or they seem to be acting, or they seem to be converging at the point G, which is the resultant location or the center of the gravity. So this resultant force, that is 4 Newton, is acting at the center of the gravity, as you can see. For the figure above, by taking the moment about A and B, we see that the moment, if you take the moment about A, we can see that, and then you take the moment about B, the resultant weight or the resultant moment, they seem to be acting from point G. So also note that the sum of the moment due to the individual particle weight about point G is equals to 0, meaning that the clockwise moment about G is equals to the anti-clockwise moment about the same G. That is, if you take G to be the center of gravity in this case, or the point whereby you are taking the moment, so because of A, which is 1 Newton, A times 3 meters, that is 1 Newton times 3 meters is equals to 3 Newton meter. And from B, you can see that we have 3 Newton, we multiply by 1 meter, which is 3 Newton meter. So the clockwise moment is equals to the anti-clockwise moment, while we take the moment about section G. Similarly, the center of the mass in this case is a point also, but this point is a point that located the resultant mass of a system, of a body, or a particle. Generally, it is located, is the same as G, meaning that the center of the mass will coincide, that is, generally they will coincide with the center of gravity. But generally, the center of the mass is the point at which the resultant mass of the system or body seems to be acting, or that is located. Then on the same note, we need to know about the centroid. When we are looking at the centroid, it is a point also. Centroid is a point, but this point defines the geometric center of an object or a body. That is the center of that object, or the center of that body is the one that is termed as the centroid. So in this case, the rectangular that you see here, the rectangle that you can see here, the x-axis and the y-axis, they are intersecting at the center of that rectangular section. And in this case, that center of this section where x and y axis coincide is the one that is termed as the centroid of this rectangle. So the centroid coincides with the center of the mass or the center of gravity only if the material of the body is homogeneous, meaning that there is a possibility whereby the center of the mass, the center of the gravity, and the centroid coincide or share or one point or the same location. Or in another one, because the center or the centroid is not changing, then we can say that the center of the mass and the center of gravity, there is a possibility that they are going to occur at the center of this object or the centroid. This only happens when the material is homogeneous. The material that is making this item or this object is homogeneous, meaning that the density of the specific weight is constant throughout the body. You can see this triangle, which is here. We can see the location of the center, or that is the centroid, which is C. It is at a third from the base. That is what we know, that the centroid of a triangle is a third from the base. That is something that we need to know. But then you need to know how to grade it. If an object has an axis of symmetry, meaning that it is symmetrical in nature, then the centroid of the object lies on that axis, or it lies within the axis. And therefore, I have this object which is cylindrical in shape. The x, the y, and the z axis, they are going to coincide at the centroid. Reason being, it is a symmetrical object, and therefore along the axis of symmetry, that is where we obtain the centroid of that object. In other cases, the centroid is not located on an object. It, as you can see from this diagram, the centroid is somewhere outside the center of that object. That is, when we have an arc, the one that is bridge in color, that is an arc, you can see that the centroid is not located anywhere along that arc. It is just in the space. That occurs when we have this kind of a shape or this kind of an object. We can consider a system of n particles as shown in the diagram below. The net or the resultant weight is given by W times R. R is the resultant weight, you multiply by W. So the summation of all the weight is the one that is going to give us the resultant weight of that object. So if we sum the moment about the axis, which is y-axis, as you can see from that diagram, then we get XWR, meaning that along the that is from y to x, we multiply by WR. WR is the resultant, weights. So that you multiply x1 with W1 plus x2 times W2, x3 times W3 all the way to xn times Wn. X is the distance from the y-axis, while W is the weight. So X is the distance of its respective weight from the y-axis. So you multiply, moment is force times the distance. So distance times the force. That is x1, for example, times w1. X1 is the distance from y to the point where we have w1, which is the weight for 1. So if you multiply the 2, you get the moment due to that w1. So you sum all the way. So you sum all the moments so that you can have the resultant moments. So similarly, we can sum moment about x and about the z-axis to find the coordinates or ordinates of G, such that if I want to know the value of x bar, which is the ordinates for the ordinate for all the centroid, then it is the summation of x bar w over summation of w of all the weight. Y bar is summation of y bar w over summation of w. Z bar is the z bar, the summation of z bar w times over summation of w. Then we need to replace, by replacing w with m, then this equation, the coordinate of the center of the mass can be found. We just need to replace w with m so that we can be able to get the coordinates for the center of the mass. That one you can do more with your lecturer during your face-to-face class. Then a rigid body can be considered as a makeup of infinite number of particles. Hence, using the simple principles as we have done previously, we get the coordinates of G by simply replacing the discrete summation of the continuous, as you can see from these equations. So there are 3 ways upon which we can be able to locate the centroid, or we can be able to determine the centroid. One of them is by use of graphical methods. Then we have geometric methods, and then we have the method for the moment. Those are the 3 ways upon which we can be able to determine the centroid of a plane in geometric area. And then you are going to do with your lecturers on how the steps for determining the area of the centroid, because it is not practical for us to be able to do it online. So you are required just to choose an elementary that is the appropriate differential element with the dA, which is the area for that. And you need to choose it at a general point, which is xy. Then from there, you need to express it in terms, that is x and y, you need to express them in terms of a simultaneous equation, as you can see. Then use a vertical rectangular element. If the converse is true, then use the horizontal rectangular elements. We are going to see, or you're going to do with your lecturer during your face-to-face class. Then express dA in terms of the differentiating elements, dx and dy. Then from there, you need to determine the coordinates, that is x bar and y bar of the centroid of the rectangular element in terms of the general points, which is x and y. Then you need to express all the variables and integral limits in the formula using either x or y, depending on whether the differential element is in terms of dx or dy respectively, and then you integrate. I think this one you can do with your lecturer. So this is one of the examples that we need to do, or we need to use in calculation. Here you are required to calculate the centroid of this figure. And this is a regular figure, as you can see. So the first thing is that you need to subdivide into 2 the uppers, the 2 rectangulars that is the rectangle which is above and rectangle which is below. That one you can be able to do it. So the first thing is that you need to determine YC and XC. That is what we are supposed to do, so that we can come up with the ordinates that are required for us to be able to define the centroid of that figure. So how do you go about it? The first thing is that you need to note that the YC can be given by the summation of AY, A times Y, you divide by the summation of all the areas. XC can be given by the summation of all the areas times the value of X, you divide by the summation of areas. That is exactly what we are supposed to find. That is OXC and YC. XC is for the ordinates for the X part of the centroid, and YC is the ordinate for the Y part of the centroid. So Y1, Y2 will be the Y1 will be for the first. That is, we need to divide this into two, 1 and 2. So Y1 is the distance from the left lens to Y1, and Y2 the same case. So if you can get 412, you divide by 2, that means that only the upper section, that is, it is subdivided here. We are subdividing it along this point, so that we have the lower rectangle, and we have the upper rectangle. So you need to divide Y1 is for the down rectangle, and Y2 is for the upper rectangle. So Y1 is going to be given by 412, you divide by 2, which is 206. Y2 is going to be given by 615, you minus 412, so that you get whatever is on the top. Then we add to 412, because at the bottom is whereby we have the reference. The reference is along that line, which is region 335. So that Y2 will be 513.5. Then A1 is the area, which is 335. You multiply by 412, you get that. A2 is 130. You multiply by 615 minus 412, so that you get that answer. Then you multiply A1 with Y1, A2 with Y2, and then you sum all AYs, that is A1, Y1 plus A2, Y2, so that you get an answer. Then you sum all the areas, that is A1, A2, you sum them. Then you divide the two AY summation, you divide by the summation of A, so that you get the answer for YC that is required. The same case is you are supposed to follow for the case of XC, but in this case, as XC is going to come from the left hand side, that is the line 412 will be the line which is the reference. So you need just to follow the same procedure, so that you can be able to obtain that YC, and then you just go to YC, comma, YC, and that is XC, comma, YC. Those are the ordinates of that centroid. So this is just the summary of A, that is element 1 and 2. You have their areas, you have their Y, you multiply, and then you get that section. Then you have the X, you have all the A times X, you get that one. Then X and Y will be our ordinates. Will be our ordinates. Then from there, we need to know how to calculate the second moment of area, which is also called the inertia. That is the inertia, moment of inertia. So also termed as the moment of inertia of shape of a body. And we know that when you have the moment of a force, it is force times the perpendicular distance from an axis. And then when you have the moment of mass, it is mass times the distance from the center of the gravity. And therefore, when we have the moment of area, it is area times the distance from the centroid. So when we have the second moment of area is whereby we have the area multiplied by the distance squared. And the units are in millimeter to power 4. Millimeter to power 4. So second moment of area is whereby we have the first moment of area, and still we have the second moment of area. The first moment of area is area times the distance from the centroid. The second moment of area is area times the distance from the centroid squared. That is what you need to know. And this information can be able to give you more about what you need to know. So we are considering a flat section, sectional area at a distance from the axis. We have the axis, which is SS, which is at a distance. An object is a distance y bar to the centroid, and you need to know how to determine the second moment of area. How do you go about it? One, G, we are saying is the centroid, which is at a distance y from the axis SS. Then the axis you need to draw a parallel line through through G. In this case, it is GG. That parallel line is parallel to the axis, which is SS. And then from there, you need to determine the first moment of area, which is the product of area times the distance y. That is the distance, the area of that figure, the shaded section. You multiply by y bar so that you can get the first moment of area. Any quantity multiplied by the distance from SS twice result to the second moment, and therefore area multiplied by the distance where the distance twice is the second moment of the area, which is given by value I. Unfortunately, the area in the mass spread, that is unfortunately area in the mass, the spread allowed, they don't exist at one point. And therefore, for us to be able to use the centroid in calculation of the second moment of area, that is being ambiguous. And what are you supposed to use? You are supposed to use the radius of dilation, which is given the value K. And this is used to eliminate that, that is to eliminate the effect that is brought by the mass, spread of mass and area from squaring the distance from the centroid. So it eliminates by using the radius of dilation of that is K, it eliminates the resultant effect emanating from squaring the distance from the centroid, and therefore the second moment of area will be given by A times K squared, where K is the radius of dilation, as we are going to see. And then we are going to see that there is a formula that we use in calculation of K, in that case. So we are required to determine the first and the second moment of area in this case. And as you can see, the breadth is B. We have that strip horizontal. We have Y, the distance to the central, to the element from that SS, which is the axis. And we have the distance dy, which is the depth, the thickness of that strip, that consideration. So the area of the strip is B times dy. The first moment of area is Y times dA, which is dy dy. The second moment of area is Y squared dA, because the distance squared multiplied by the area, which is by squared. For the whole section, then we needed to integrate. We need to integrate so that we can obtain for the whole oval, because whatever you have obtained is the area for the strip, or the second moment of area for the strip. So we needed to integrate that so that we can obtain for the whole, and therefore we need to know how to do the limit of integration from bottom to top. And then you can watch those two videos in order for you to be able to determine that. in order for you to be able to determine that. And then you can use this example for you to be able to know how to calculate the centroid by use or the second moment of area. Then these are the second moment of area for standard shapes. As you are going to see, you can check them from there. Then there is another thing that is called the radius of gylation. And when we are looking at the radius of gylation, what you need to know is that it's also called the radius of a body, radius of the body. It is a radical distance, it's a radial distance to a point which would have a moment of inertia the same as the body actual distribution of the mass if the total mass of the body were concentrated there. This structural design, in structural design, the radius of gylation is computed as you can see from that formula Rg, which is the radius of gylation, or can just give it K, is going to be given by the root of the second moment of area I over A. A is the area of the material, and by doing so, we can be able to obtain what is the second moment of area. Before we terminate, it is good for us to be able to watch this video. We watch this video, and let me just copy. Let me just copy. Then we stop sharing so that I can share another screen. So that I can share another screen. So that I can share another screen that is going to give us the whereby we can be able to let me see if we can be able to watch this video. It is not possible for us to watch this video. I thought that it was possible, but whatever I'm obtaining is something that is different. So we are not going to watch that video. You can just do it with you can just try to do it by your own, and then we are going to terminate our lesson at that point. Thank you for listening. God bless you.